This is just a very short video about the concept of linear dependence and linear independence. It's easiest to think about this at the start in very concrete terms. Imagine I give you a set of three vectors, 1, 0, 1, 1, 3, 4, and 2, 3, 5. A linear combination is a real number times the first vector plus a real number times the second one plus a real number times the third one. If I were to pick C1, C2, and C3 all to be 0, I would get the 0 vector, the column vector that has zeros in all of its positions. What we're interested in, is there any other way of doing this? Is there a selection of values for C1, C2, and C3 so that they're not all 0, and yet this happens anyway? If there's a way of doing that, then we say that the set of vectors is linearly dependent, and if not, if the only way that I can make this happen is by making all the C numbers 0, we say that they have a linear independent set of vectors here. So supposing I have a linear combination of these three vectors that comes up equal to the 0 vector. We've decided how to multiply numbers by column vectors and how to add vectors together. So doing all of the arithmetic, when the dust finally settles, this vector has to be the vector 0, 0, 0, meaning that each one of these quantities must be 0. This gives us a system of linear equations to look at in which the names of the variables are C1, C2, and C3. We'll deal with this situation by using our augmented coefficient matrix idea. Writing out the augmented coefficient matrix, I see that there is some good news. I already have a 0 in that spot, so I don't have to do anything to it. Also, the first number in the top row is 1, likewise the third row. I'm just going to subtract row 1 away from row 3, and after doing this and doing the arithmetic, I get this augmented coefficient matrix. An observant person will notice there's going to be some trouble here, but in case you didn't, I'm going to take row 2 and subtract it away from row 3. 0 minus 0 is 0. 3 minus 3 is 0. 3 minus 3 is 0. And 0 minus 0 is 0. If I go back to thinking about this as equations, that last equation says 0 times C3 is 0. That equation is true even if you just pick the value of C3 at random. So C number 3 can be chosen to be anything you feel like. If I back up in the previous equation, this says that 3 times C2 plus 3 times C3 must be 0. That says that 3 times C2 is the negative of 3 times C3. Divide the 3 out. C2 must be the negative of C3. Backing up to the top equation, it says that C1 plus C2, which is the negative of C3, plus 2 times C3, whatever that is, must be 0. This says that C1 plus C3 must be 0. C1 is also the negative of C3. You can pick the C3 to be anything you feel like, and then C1 will be the negative of that, and C2 will also be the negative of C3. I'm interested to know if there's any way to do that where the numbers don't all come up 0, and the answer is obviously yes. The easiest thing I can think of is make C3 negative 1, then C2 will be 1, and C1 will also be 1. there are non-zero numbers in the sense they're not all zero. In this case, none of them are zero. So that if I use those as coefficients in my linear combination, I get the zero vector. So if I wanted, I could represent my result this way. Suppose that I took a linear combination of my three vectors. I'd have a times the first vector, b times the second vector, plus c times the third vector. But I also have this linear dependent thing going on. If you add 2, 3, 5 to both sides and subtract 1, 3, 4, you find out that 1, 0, 1 is actually a linear combination of the other two vectors. In my linear combination of my three vectors, I could literally write 1, 0, 1 as that, and then after doing the arithmetic, I find out that a linear combination of my three vectors is actually always going to be a number times 2, 3, 5, plus a number times 1, 3, 4. Every linear combination of the three vectors is a linear combination of these two vectors. In a certain sense, the contribution of 1, 0, 1 is nil. It contributes nothing. It brings nothing to the table. But on the other hand, think of making a linear combination of just 2, 3, 5 and 1, 3, 4. I can trivially write that as a linear combination of all three of my original vectors by saying the coefficient of the 1, 0, 1 is 0. The first thing that we showed was that the span of these three vectors is contained within, is a subset of the span of these two vectors alone. But now we see that the span of these two vectors alone is a subset of the span of all three vectors. This set is a subset of that one, and that one is a subset of that one. This means that the two sets are equal to each other. If I look at all of the linear combinations of the three vectors I started with, it is the same collection of vectors as all of the linear combinations of just these two alone. If I'm interested in span, the span of sets of vectors, and my set of vectors is actually linearly dependent, what that means to me is I've got some vector in my set, at least one of them, that I can just stop writing down. This makes the set of vectors that I have to deal with smaller and therefore easier to deal with. We'll talk more about this as we go along. I hope everybody's having a good day. I'll talk to you again soon.